To understand why particles have mass, we have to discard the idea that they are infinitely small points. Instead, the building block of reality is a one-dimensional, tensioned string of time. When this string deflects, it twists and folds back on itself to form a perfectly closed, vibrating toroidal loop. That topological knot is the particle. For hadrons, the particles inside an atomic nucleus, that knot takes a specific shape, the T3 toroid. The field geometry forms a continuous Mobius band shaped like an equilateral triangle. As the surface twists, the tension pulls the three street edges inward, creating a shallow 2-degree concave indent on each side. But the triangular surface is only the boundary. The particle itself is the wave traveling along that surface, the Hamiltonian path. This path traces a distinct Y-shaped trajectory. As the path travels down the corridor, the Mobius twist rotates the triangular surface itself. At the midpoint between corners, the face of the toroid has rotated until it is angled toward the very center of the triangle. To remain on the surface, the path must follow this inward tilt, diving toward the center before the next corner forces it back outward. This means the Y-shape is not an arbitrary design choice. It is a physical requirement of navigating a rotating Mobius interior. Wrapping a continuous wave around this heavily warped topology requires extreme precision. If the wave's phase does not align exactly with the geometry by the time it completes a circuit, it will destructively interfere with itself. This geometric rotation creates a strict environment where the particle's trajectory and its phase are mathematically locked. The Y-path emerges as the only viable route through this hyperbolic space, providing the foundation for how we track the particle's phase. To find the exact phase modulus that allows the wave to close cleanly, we look for the smallest integer that satisfies the geometry of the twisted triangle. That number is 30. 30 is the unique minimum value that simultaneously satisfies 5 rigid closure constraints: integer winding around the torus, a 720-degree spinor double cover, chiral Mobius compatibility, coprime numerators for stable winding, and a 5-fold symmetry. When waves propagate around this 30-step lattice, any wave vibrating at a composite frequency, like 2, 3, or 15, eventually overlaps with its own subcycles. These composite modes perfectly destructively interfere, canceling themselves out of existence. The only frequencies that survive are the ones that share no common factors with 30. These are the coprime modes: 1, 7, 11, 13, 17, 19, 23, and 29. Exactly 8 modes remain. These 8 mathematically derived coprime lanes map precisely to the 8 fundamental gluons of SU3 color charge. This chart displays actual, published spectral data from lattice QCD, tracking the peak heights of gluon states. When overlaid with the geometric projection ratios derived purely from the mod 30 structure, the numbers match to 4 decimal places. The 8-gluon spectrum follows directly from wave interference on a 30-step lattice. The geometry of the T3 toroid dictates the count. This geometric framework directly addresses one of the hardest open questions in physics, the Clay Mathematics Millennium Prize problem. The challenge is to mathematically prove that Yang-Mills theory possesses a strictly positive mass gap above the vacuum. A topological perspective suggests the mass gap is a rigid boundary condition. This bypasses the need for the infinite non-perturbative loop corrections that have stalled standard field theory solutions. The geometric proof requires 6 steps. Step 1 is restriction. Any valid gluon winding must adhere strictly to the 8 coprime modes of the mod 30 lattice. Step 2 is positivity. This graph plots the projection weight function of the particle onto its winding lane, calculated as sine squared of r times pi over 15. Every single valid coprime point on this curve floats strictly above the zero line. Because every value is positive, the system natively satisfies the reflection positivity axiom of quantum field theory. Negative energies are mathematically prevented, ruling out tachyons and ghost modes. Step 3 analyzes the singlet. The colorless state of the strong force sits exactly at the origin point of this graph, where r equals 0, and the sine squared of 0 is exactly 0. Step 4 applies Shor's lemma to the r equals 0 state. This determines how highly symmetric systems interact with the lattice. Because this r equals 0 state is completely symmetric, possessing 0 phase rotation and 0 Noether charge, it physically cannot sustain a conserved current. It commutes entirely with the rest of the lattice. A wave state that cannot be mathematically produced or absorbed by the lattice physically cannot propagate. Zero-energy gluons are topologically forbidden from existing. If a zero-energy state is strictly forbidden, what is the lowest possible energy a propagating gluon can actually possess? Step 5 establishes the floor. The lowest available states on the mod 30 lattice sit at the extreme boundary lanes of r equals 1 and r equals 29. A particle's shedding energy hits this hard floor and can drop no further. The algebraic value of this boundary floor is exactly sine squared of pi over 15, yielding a unitless projection weight of approximately 0.043. To find the actual mass of this gap, we must scale this geometric ratio against the fundamental constants of the strong force. We use the QCD energy scale, lambda, which represents the natural mass of the proton, and the infrared coupling constant, alpha, defining the force's strength at its lowest energies. Step 6 calculates the gap. Multiplying the geometric floor by these constants converts the ratio into a physical mass, yielding a minimum propagation energy of roughly 184 MeV. This aligns with experimental reality. A glue ball, a bound state of gluons, should be a multiple of this value. The predicted scalar glue ball at roughly 1.5 GeV represents the mass of approximately 8 of these gap quanta. This mass gap does not rely on complex dynamical suppression. It is purely algebraic. Scaling the system to the continuum limit doesn't change the outcome. You can shrink the lattice spacing infinitely, but the sine squared of 0 will always equal exactly 0. The gap cannot close. The Yang-Mills mass gap is a hard topological boundary condition enforced by geometry. A string cannot have zero tension, and a closed system cannot propagate a wave with zero phase. Field theorists often raise a specific objection. If you pump extreme thermal energy into the system, wouldn't that eventually force the mass gap to close? By calculating the standard thermodynamic partition function for the discrete lattice, we find the exact same gap energy derived by the geometric proof. The zero state remains energetically forbidden. At extreme temperatures approaching 155 MeV, the physical system undergoes QCD deconfinement. The highly ordered lattice structure vibrates apart and dissolves into a chaotic plasma. But thermal deconfinement is distinct from gap closure. As the physical structure passes its thermal limit, individual modes break out of confinement, but the mathematical zero line sits completely isolated and inaccessible. The interference balance frequencies of this all-integer winding sum map directly to the distribution of prime numbers. As shown in this equation, the topological energy scale of the entire system equals the mass of the up quark divided by the first Riemann zero. The mass gap is an unyielding property of the zero-temperature quantum vacuum. Pumping thermal energy into the system will deconfine the structure, but no amount of heat can force a topological gap to close. This exposes a structural flaw in how standard continuous field theories attempt to define the standard model. The mathematical axioms that govern these fields, specifically the Osterwalder-Schrader axioms, demand a property called O4 Euclidean covariance. Physically, O4 covariance means a system must remain perfectly invariant under both spatial rotations and spatial reflections, meaning you can turn it inside out like a mirror flip with zero structural change. Experimental data contradicts this assumption. The weak nuclear force explicitly violates parity, meaning the physical universe is chiral. It behaves differently in a mirror. Which brings us back to the Mobius toroid geometry we established earlier. A continuous Mobius band natively resists O4 symmetry. If you force a spatial reflection on a Mobius structure, it inverts its native chirality, shattering its own mathematical rules. The mathematically rigorous continuous symmetry for a chiral universe is actually SO4. This allows for endless spatial rotation, but strictly forbids spatial reflections. When you take the discrete mod 30 lattice and coarse-grain the angles out to an infinite continuum limit, the discrete rotations average out. The system perfectly recovers continuous SO4 symmetry while natively preserving its chirality. The framework predicts this charity violation by design. It does not treat chirality as an experimental anomaly that has to be hand-coded into the mathematics after the fact. Geometry dictates that parity violation is natively embedded into the fundamental forces. The Millennium Prize mass gap, the 8-gluon spectrum, and chiral parity violation function as the unified consequences of modeling reality on a